This chapter is a continuation of what we started in chapter 6 with more methods of how to bias the transistors on. Let's begin where we left off. Let's look at the base and see that VBB is 2.5 volts. So voltage at the emitter then is 2.5 volts minus zero point 0.7 volts for the diode drop, which equals 1.8 volts. We come now to a very important concept, and that is that we are going to agree that current through the collector is approximately equal to current to the emitter. And the reason why that is that current through the emitter includes current from the base, which is so small, is usually in the microamps, that we're just going to forget about it and say that current into the collector is equal to current through the emitter. Now we calculate current through the collector by saying is voltage on the emitter divided by the emitter resistor, which is 1.8 volts divided by 1.8 kilo ohm, and that equals 1 milliamp. We now proceed as before, where we need to find VRC, the voltage drop across the collector resistor, and that's 1 milliamp times 10 kilo ohms, or 10 volts. Then we find voltage at the collector with respect to ground, that's VC equals 20 volts minus 10 volts, which equals 10 volts. Finally, we find voltage CE, that is voltage at the collector minus voltage of the emitter. So that's 20 volts minus 1.8 volts. It equals 8.2 volts. That means that this transistor is active. This is an active transistor circuit. Here is an interesting problem because if you notice, we have an LED in the collector circuit instead of a resistor. Even so, we proceed as before. Voltage on the emitter equals voltage VB minus zero point 0.7 volts, or 2 volts minus zero point 0.7 volts, which equals 1.3 volts. Remember, we agreed that current through the emitter is equal to current through the collector, but in this case, current through the LED is also equal to current through the collector. So then we go and calculate this current by saying that it's VE divided by resistance in the emitter, or 1.3 volts divided by 100 ohms. This equals 13 milliamps. This circuit is called a current source, and it's very useful because it doesn't matter that we change the LED with another device. The circuit will always deliver 13 milliamps through whatever is in the collector circuit. We're going to call this in the future, we're going to call it the load. In other words, the LED is the load. So we're putting 13 milliamps through the load. The voltage divider bias circuit is the one that's most often used to bias an NPN transistor. Look carefully at the circuit and you will notice that the base is connected to the 2.2 kilo ohm resistor. To calculate the voltage on the base, we use the voltage divider equation. We say 2.2 kilo ohms divided by 10 kilo ohms plus 2.2 kilo ohms and multiply it times 25 volts, which is VCC, equals 4.5 volts. That means that the voltage on the base is 4.5 volts. Next, we find the emitter voltage by saying it's 4.5 volts minus zero point 0.7 volts, and that equals 3.8 volts. We agree that collector current is equal approximately to emitter current, which is 3.8 volts divided by 1 kilo ohm, which is 3.8 milliamps. The voltage dropped across the collector resistor VRC is equal to 3.8 milliamps times 3.6 kilo ohms, which is 13.7 volts, which means that the voltage at the collector with respect to ground is 25 volts, or VCC, minus 13.7 volts, that equals 11.3 volts. Finally, we say VCE is equal to VC minus VE, which is 11.3 volts minus 3.8 volts, that equals 7.5 volts, a positive number, which means that this is an active transistor. Now we can define a new unit, and that is the quiescent point, or the Q point. And the Q point consists of two things: current in the collector, which is 3.8 milliamps, and voltage collector emitter, which is 7.5 volts. We need to do a few more calculations on this problem, and the first thing is we need to find VCE off. And VCE off is the same thing as cutoff. And if you remember, if there is no current to the base, then there is no collector current. And in that case, VC would be the same thing as VCC. In this case, V cutoff is 25 volts. Now we need to calculate the maximum current that can flow in the circuit, and this is called saturation current. And in order to calculate saturation current, I take and draw a jumper, an actual little piece of wire between the collector and the emitter. This way we're going around the transistor. And in that case, the maximum current is calculated as VCC divided by RC plus RE. In other words, 25 volts divided by 3.6 kiloohms plus 1 kiloohm, which equals 5.43 milliamps. Now we are ready to plot the DC load line, and that consists of voltage collector emitter and current through the collector in milliamps. Take the value of VCE cutoff and plot it on the graph. Also take the value for current saturation, also plot that on the graph, and then take and draw a straight line from the saturation current point to voltage cutoff. Finally, take the value of Q point that we had calculated and then also plot that on the load line. And the idea of this is that the Q point should be somewhere in the middle of the load line for the transistor to be operating properly. And it looks like in this case, the transistor is a little bit above the midpoint, but still not bad.